Hi folks, this is a lesson on antiderivatives. It's our first lesson of Unit 6. And so let's begin here by remembering that if you are taking a derivative of f, you get f prime. You take a derivative of f prime, you get f double prime. An antiderivative means going the other way. So the antiderivative of f double prime is f prime, and the antiderivative of f prime is f. So it's like f and f prime are in a relationship. F prime is the derivative of f, and f is the antiderivative of f prime. Thinking of the ladder that we've talked about so many times in class, you know from the fall that, if you have f, you go down the ladder by taking a derivative, right? So you take a derivative, you get to f prime, another one f double prime, another one f triple prime, and we've even talked about how you can go on doing this, and the next or the fourth derivative of f would be called f and then parentheses 4, like that, okay? Now, we're now telling you that if you go up the ladder, that means you are taking an antiderivative, right? So the antiderivative of f prime is f, and the antiderivative of f double prime is f prime. And the antiderivative of little f, we're going to introduce a big F to denote that. So the antiderivative of little f is going to be big F. So when we think of a function like little f, a specific function, f is equal to x squared, if you think about this for a little while, you are going to figure out that the antiderivative, big F, must be the function 1/3 x cubed, so that when you differentiate that, you would get x squared. And then if you think about it a little bit more, you're going to realize that, really an antiderivative of x squared could be 1/3 x cubed plus any number. If you tack on a number here, when you differentiate, the number is going to go away. So you can tack on any number on the end of the 1/3 x cubed, and that's why we say that we have this concept of the general antiderivative, which is the function big F plus any number, plus c. The c is a constant, and it just means any number. So big F is going to be the antiderivative of little f, and the most general one is going to be big F plus c. So for this little f, which is x squared, we would say the big F, most general antiderivative, would be 1/3 x cubed plus c, okay? Okay, so now that we know that we can go up the ladder, and that antiderivative just means undifferentiating or figuring out what function was above on that ladder, we are going to just practice doing that. So if you think of our trig functions, pause the video and see if you can figure this out. If f is equal to cosine x, right, little f is cosine x, what is big F? If little f is sine x, what is big F? So pause the video and see if you can figure those out. Okay, so hopefully you got these answers. The one that's a little bit tricky is this one, right? So if the little f is sine x, then the big F has to be negative cosine x, because when you differentiate cosine, just differentiate cosine, right, you're going to get negative sine. But then if you want the final answer to be positive sine, you have to have a negative to start with. So pay attention to that one. The rest of them, it's literally going backwards. The derivative of tangent is secant squared, for example, so the antiderivative of secant squared is tangent, and we need to remember to put on the plus c for the general antiderivative. Okay. Power functions. A constant like 1, you can think of it as x to the 0. That's why I have it under power function. But we know that the derivative of x is 1, right? So the antiderivative of 1 is x. The derivative of x is the derivative of x squared over 2 is x, so the antiderivative of x is x squared over 2. Pause the video and see if you can figure out the next few here with the powers until, let's go until here. Pause the video and see if you can. Okay, so hopefully you came up with, x cubed is x to the 4th over 4 plus c, and x to the 4th is x to the 5 over 5 plus c. Always remember, there's no reason to ever make a mistake on an antiderivative, because you should be able to take the derivative and get the answer, going to the right here. So for example, if you think that x to the 5th over 5 plus c is the antiderivative of x to the 4th, well, let's just check that. Take a derivative, right? So the c is a number that's going to go away when I take a derivative. And then I have 1/5, that's this constant here. And then x to the 5th will become 5x to the 4th if I'm taking a derivative. The 5s are going to cancel, and yeah, I would get x to the 4th. So I know that I have the right answer there. Now, if you're paying attention to the pattern, you're realizing that for a power of x to the n, it looks like our antiderivative is coming out to be x to the n plus 1 over n plus 1 plus c. So we are adding 1 to the power, so it becomes x to the n plus 1, and then we're multiplying by the reciprocal of that, right? The reciprocal of n plus 1 is 1 over n plus 1. And of course, we can, simplify that and write it like this, but really that's what we're doing. Add 1 to the power and multiply by the reciprocal, and that gives us the famous reverse power rule for anti-differentiating a power. Now, the reverse power rule works for negative powers. I'm going to skip this exception for a minute. I'll come back to it in a minute. But it works for negative powers that are not -1. Okay, I might as well do the exception. The exception to the rule is 1 over x, right? 1 over x means x to the -1. So if you try to add 1, right, this is now my n in the reverse power rule. So if I add 1 and I try to do the rule that I just said, well, I'd get -1 plus 1, which is 0. So if I try to go x to the 0 over 0, I'm going to quickly realize I cannot do that because you can never divide by 0. So this is going to remind you that this is the exception to the rule, because the antiderivative of 1 over x is ln, the absolute value of x, plus c. Okay? The reason we are saying absolute value of x is, I'll just go here quickly to explain that. You might remember from the fall that the derivative of ln x is equal to 1 over x. And if you think of the graph of ln x, that makes a lot of sense because, imagine just sketching your derivative of this graph, right? And you would go, if this graph is f, then f prime would be, well, you have a very steep slope here, right? So it's a very high number for f prime, and then the slope is getting less and less and less until it becomes very small and almost 0, right? So that you can even sketch the the derivative, sketch the derivative. If f is ln x, then f prime is 1 over x. So we know that from the fall. All that we're saying is that if f is ln of the absolute value of x, then the derivative is also 1 over x, because this graph, ln absolute value of x, looks just like the ln x graph, except you can flip it on the other side, right? Usually we say, oh, the domain of the ln x graph is x greater than 0, right, for this ln x. But if you take an absolute value before you do the ln, well, then you can put in positive and negative numbers into the ln, right? So you get a graph. I've been a little sloppy here, but this graph really should be symmetric. It's just the exact same on the two sides here, right? And the derivative on this side would look like this, and on the other side it would look like that. So it's the 1 over x function, right? So that's why the way to write the antiderivative of 1 over x is going to be ln of the absolute value of x. Okay. Let's go on to negative powers. So if you have 1 over x cubed, then this is x to the negative 3. Power rule just works great. And we go x to the negative 2. That's negative 3 plus 1. And we're going to divide by that negative 2 and write it out front as negative 1/2. You can pause the video and do the rest of these, please. Okay, so check your answers here. You got to know how to add 1 to a fraction. So for example, 1/5 plus 1 is 6/5. So there's my new power here if I'm anti-differentiating x to the 1/5. And then the reciprocal of 6/5 is 5/6. Please realize that there's no negative sign when we when we say reciprocal. That does not involve changing the sign. It just means flipping the function, right? Or if you have a whole number like 4, right here, then the reciprocal of 4 is 1/4, right? Just to say it again, to be clear, the reciprocal of 2/3, right, is 3/2. Okay, there's no negative sign that gets introduced. Okay, let's see. Going on here, pause the video and see if you can figure these out for antiderivatives of inverse trig and exponentials. Okay, so check your answers. Hopefully you got them correct. Here for the inverse trig, it's really a matter of memorizing, right? You know that the derivative of tangent inverse or arctan, that's two ways to say the same thing, the derivative is 1 over 1 plus x squared. So then the antiderivative of 1 over 1 plus x squared must be arctan x plus c. So these right here, you're just memorizing, really, going backwards from the derivative. These also, it's mostly just remembering, you know, the derivative of e to the x is e to the x. So the antiderivative is the same. Derivative of 2e to the x is 2e to the x. So the antiderivative also is the same. Just tack on the plus c each time. 2 to the x, just remember if you want to differentiate and just get 2 to the x without anything, no constant next to that. So then since the derivative of 2 to the x, let's differentiate what I wrote here, right? The derivative of 2 to the x is 2 to the x ln 2. So if I have 2 to the x divided by ln 2 to start with, then my final answer will be 2 to the x, which is what I want, right? So the antiderivative of 2 to the x is 2 to the x divided by ln 2 plus c. Okay, so we've talked about the general antiderivative, that is the big F plus c. We could also talk about a particular antiderivative, which is going to be cases where we find the c. We find the constant using what we call initial or boundary conditions. And I'll give you examples of how we do that. Okay. So first of all, so here are a few examples of both the general and the particular. First thing I want to say is that right now we only know how to anti-differentiate sums and differences, right? If you have for example, something, sine x times x squared, if that's your f, then you cannot just do big F is equal to the antiderivative of that times the antiderivative of that. That will not work, right? However, if things are just added and subtracted, we can do the problem just piece by piece. So that's all we know right now, how to do additions and subtractions. We'll just do them piece by piece. So this first one is going to be 4x squared over 2, and then the 4 and the 2 will cancel to make 2. So I'll get 2x squared plus, I have to rewrite this as x to the 5 over 2. So then the antiderivative, be careful not to differentiate. You're anti-differentiating, so it becomes 2/7 x to the 7/2. Add 1 to the power and multiply by the reciprocal. I'm having trouble writing. 5/2 plus 1 is 7/2. Yeah, and then this guy, the negative sign is just like a constant that's going to come down, right? So negative, and then the antiderivative of 2 is 2x. And then you're going to tack on plus c. Right, so 2x squared plus 2/7 x to the 7/2 minus 2x plus c is my general antiderivative. This next one, for each of these, you may want to pause the video and then check your answer. So here you would start by realizing, first of all, I'm at f prime, so the antiderivative is going to be called f, and this has to be written as a power function, x to the 1/3 minus 5x squared. So then the antiderivative, piece by piece, we're going to add 1 to the 1/3 to get 4/3, and then flip that to multiply out front by the reciprocal. And then this, the minus 5 is a constant, so it will carry through, and then x cubed over 3 plus c, right? This would be my general. This is the general antiderivative. To find the particular, I can go off to the side and find c. And how do we find c? Well, we use this additional information that the problem has given us, that f of 0 is equal to 1. Well, I have f here for the most part, so I'm going to put in my x and y into that f, right? So the y is 1 when the x is 0. So 3/4 times 0, which is 0, minus 5/3 times 0, which is 0, plus c. So my c is going to be 1 for this problem, right? So then my particular antiderivative is going to be, and the question said find the particular, right? Find the particular. So I'll come back and replace this c. We have to find it, and we just found it to be 1. So the final answer is all of this. That's my final particular. Let me draw that box better. Let me erase the word general, because now it's not general because I found the number. This right here in red, along with the +1, is my particular antiderivative. Okay, this next one, the function is little f, so the antiderivative will be big F, and it'll be x cubed over 3 plus, or minus, really, tangent x, minus tangent x plus c. And then go off to the side to find the c. Use this x and this y to say 0 is equal to 0 minus tangent of 0, which is 0, plus c. So c is equal to 0. So in this case, the particular antiderivative, you just can erase the c, and this will be your particular antiderivative. Okay. The next one here, g prime is equal to this glob. Now, the glob is made up of something plus something else, right? So, we can definitely find the antiderivative of 4 sine x. That's just negative 4 cosine x. Here, though, you do not want to just take the antiderivative of the top, right? So do not take AD of top divided by AD of bottom, because that does not work. We don't know how to do quotients yet. We have to make this into something that we know how to take the antiderivative of. And so I would suggest that we rewrite this as 4 sine x plus x to the negative 1 times 2x to the 5th minus x to the half. So it's 4 sine x plus 2x to the 4th minus x to the negative 1/2, right? So I've written this as a power, and then I've distributed that power through, so that now I have addition and subtraction of power terms, and I can now just find my antiderivative with what we've been saying above about the reverse power rule, right? So this becomes 2/5 x to the 5th. This one, negative 1/2 plus 1 is equal to positive 1/2. The reciprocal of that is 2. This negative will carry through, and I'll get negative 2x to the 1/2 plus c. We're asked to find a general antiderivative, so that's my answer. Okay, this guy here, we're going up twice, going up the ladder 2 times. So if you have f double prime and you take an antiderivative, you get f prime, and the antiderivative of that's going to be f. So the question says find f, and it gives us 2 conditions, so that at each stage of going up the ladder, you can find the constant, right? So first, let's go up the ladder once from f double prime to f prime, and so you would get this, f prime is e to the x plus 2 cosine x plus c. Put in this initial condition to say, well, okay, so then 3 is equal to e to the 0 plus 2 cosine 0, which is 1, right? So it's 2 times 1 plus c. E to the 0 is 1 as well. So 3 is equal to 1 plus 2, which is 3 plus c. That must mean c is equal to 0. So we can just erase this as we move up the ladder one more time to get f, right? So from here, I'll do it in red, let's do it in blue. I'll do it in blue to get f, right? So I'm going up from f prime. So f is equal to e to the x plus 2 sine x, right? Plus another c, which is not the same c. If you want to call it d, you can call it d. It's another number. And for that, you're going to use this initial condition. F of pi over 2 is equal to 0. So 0 is equal to e to the pi over 2 plus 2 sine pi over 2 plus c. Sine of pi over 2 is 1. So that must mean that c is equal to negative e to the pi over 2. That's just a number minus 2, right? So without a calculator, we cannot get a decimal for that. So we're just going to leave it like that, negative e to the pi over 2 minus 2. And that's going to be this number here. So I'll come back to my f and just replace it with replace the c with negative e to the pi over 2 minus 2. Okay, and that'll be my, this is trying to be an e right here. Negative e to the pi over positive pi over 2 minus 2, right? So it's a weird constant, but it is a constant. Okay. So that's the answer there. This next one you can pause and try. It's very similar to the ones we've been doing, and the answer is B. So check that on your own. And now we're on the last page. So rectilinear motion, which we've talked a lot about in the past, and those of you that are taking physics talk a lot about there. It's particles moving in straight lines, right? And so here we already know from the fall that if you have a position function and you take a derivative, you get the velocity, right? The rate of change of position is velocity, and the rate of change of velocity is acceleration, and the rate of change of acceleration is jerk, right? So we have our famous Svag ladder from IKEA. But we now know that we can go up the ladder by taking an antiderivative. So the antiderivative of acceleration is velocity, and the antiderivative of velocity is position, right? So I'm going to do this example B here. If A of t is equal to 10 sine t plus 3 cosine t, S of 0 is 0 and S of 2 pi is 12. Find the position function, it should really say, of the particle, right? So we're going up the ladder. We're going to say V of t is equal to negative 10 cosine t plus 3 sine t plus c. And now, the interesting thing in this problem is that it doesn't give us a velocity condition, right? Both of the conditions are position conditions. So if it did give you a velocity condition, you'd plug that in at this point and find out C. But since it didn't give us a velocity condition, we just keep going up, and we're going to find the constant after we find the position function general antiderivative, right? So we'll go to S of t and say that that's equal to negative 10 sine t minus 3 cosine t plus ct, right? This is a number. So whatever it is, its antiderivative is ct plus d, okay? That will be my S. And then I can go off and find my two constants using the two initial conditions, right? So let's put in the first one, S of 0 is equal to 0. I'll do that in blue. So 0 is equal to 0 minus 3 times cosine 0, which is minus 3, plus c times 0, which is 0, plus d, right? So d comes out to be 3. And then I can put in the other one and say, okay, so s of 2 pi. So for s of 2 pi is 12, I'll go 12 is equal to negative 10 sine of 2 pi, so that's 0, minus 3 cosine of 2 pi, so that's minus 3, because cosine of 2 pi is the same as cosine of 0, plus c times 2 pi, so that's 6 pi, right? Because my t now is 2 pi, so this will be 2 pi times, oh no, we didn't find c yet, so it's 2 pi c, or c times 2 pi, right? And it's the d, which is already known to be 3. Okay, so these two are going to cancel, and so then I have 12 is equal to 2 pi times c, so c is equal to 12 divided by 2 pi, or 6 divided by pi. Okay, so then you come back here, now you're ready to write your final answer, which will be s of t, the position function, is equal to negative 10 sine t minus 3 cosine t plus 6 over pi t plus 3, right? That's just putting in the numbers that we found for C and D. Okay, the last thing we need to know how to do is to sketch an antiderivative, right? And we have a lot of information about doing this, which we developed last semester, because last semester you had problems where I would give you a graph of f prime and I would ask you questions about f, right? So really this is the same thing we're doing here, where we're giving you the graph of little f and asking you questions about big F. We can say the same types of things we would say last semester, right? So for example, here we have the graph of little f, right? So I can say when little f, remember that the relationship between little f and big F is that big F prime is equal to little f, okay? So when little f is negative, we could say big F is decreasing, right? Because when something is decreasing, its slope is going to be negative, right? So little f now is the slope and big F is the function, right? So when little f is negative, big F is decreasing. When little f is positive, big F is increasing, right? In the fall, we would say when f prime is negative, f is decreasing, right? But now we're just going to the relationship one level above between little f and big F, but it's the same thinking, right? And so then we know a lot of other things too. We said, let's just do a little table, right? So little f and big F. If little f is positive, big F is increasing. If little f is negative, big F is decreasing. If little f is changing from plus to minus, then big F has a relative max. If little f is going from minus to plus, then big F has a relative min. If little f is decreasing, then big F is concave down, right? If little f is increasing, then big F is concave up. We know all of this from the fall. It might take a minute for you to remember or to realize that we're saying the same thing. In the fall, we would call this one f prime and this one little f. But now we sometimes are calling this one little f and the other one big F. We know that in general, we're talking about a derivative and an antiderivative, right? This side is the derivative and this side is the antiderivative, regardless of what the specific letter name we're using, right? What else do we know? We know that if little f has a minimum, right, then big F has a point of inflection, a minimum or a maximum, either one, then big F has a point of inflection. So these are all the things we know, and we can use those to draw the antiderivative here. So maybe pause the video and see if you can figure it out. You want to start at this number, right, because they've given you that big F of 0 is 1, right? So you want to start there. So just make a spot, just a tick at 1 and start your big F there. And then you're thinking, well, here little f is negative, right? Little f is negative, so big F must be decreasing. So you're going to bring this down. It's also little f is decreasing, right? So slopes are getting more and more negative, so this big F must be concave down. Then you get to a minimum on little f, so big F must have a point of inflection. So now the curvature is going to change until I get here to 2, right? And then at that point, the little f changes from negative to positive, so big F has a relative minimum, right? So, and then it has to start increasing because now little f is positive, so big F is increasing. On this first stretch here, little f is increasing, so big F is concave up. And then on this stretch here, little f is decreasing, so big F is concave down, right? So we're going to have a situation, something like it's going to come up, concave up, and then right here it's going to flip to concave down. Then here we're going to reach a relative maximum, right? So it's going to start decreasing. And then let's see, it's going to decrease until it's going to be concave down until here. And then there's another POI here, and then it's going to go doing something like this. It's going to keep on decreasing, but with less and less of a slope until, yeah, we could just put an arrow there, right? So it takes some thinking, and you have to internalize how this works, but you're doing exactly the same thing as you did in the fall. So you can pause the video and try this one, number 61, and then check out the answer. Okay, so for this one, they don't give you an initial condition. I'm going to just start the position function at 0. And then I'm going to notice that for this whole stretch here, this whole yellow stretch, my position should be increasing. So at first it's increasing, you know, the velocity is increasing the whole time. So the slope on my position graph must be increasing all the way till here. And then it looks like the position kind of the velocity flattens out. So the position must be doing a linear type of growth there. And then it's curving again, the velocity, right? But the velocity is decreasing, so that means that my curvature on the position must be also decreasing, right? So the position's doing something like this, right, where the slopes are decreasing. Here the slopes were increasing, then kind of linear, then slopes are decreasing. And then now here the velocity is 0, so the position is not changing, right, between like here. I'm not lining these up perfectly, but between there and there. And then after that, velocity is negative, so position must be decreasing. And then you reach a point of inflection here, and then the curvature is changing. And then over here, velocity is 0, so position is not changing. So something like that would be the position function for this graph, okay? All right, pause your video and write the takeaways. Okay, so antiderivative of f prime is f. Antiderivative of little f is big F. Reverse power rule says antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. Exception to the rule is 1 over x or x to the negative 1, and there its antiderivative is ln of the absolute value of x plus c. General antiderivative of x to the 1/2 or rad x is going to be 2/3 x to the 3/2 plus c. And a particular antiderivative just means that we have found the value of c by using initial conditions or boundary conditions. Okay, so hope that was a good intro to antiderivatives, and I will see you in class.